This is the second video that answers the question, what method should I use when it comes to solving angles and sides of triangles? First I asked myself, do I have a right triangle? And if I did, I used SOHCAHTOA, which is the definition of right triangle trig ratios. But many triangles are not right, so we have to ask ourselves a second question. Do I know an angle and the side opposite that angle? And if I look at this sample problem that I've been given, which is A is 17.2, and the angle A is 55.49 degrees, I am given a ratio, a side, and the angle opposite of it, and that can help me establish a ratio of sine is to 55.49 degrees is to 17.2. Now I can use that particular ratio to solve any other problem. And in this case, I have been given a second angle, which is 46.85 degrees. Which means if I use that information, I should be able to figure out what this side is over here, which we'll call, for the sake of simplicity, because it's a cross angle B, we'll call it side B. And so I can write sine of 46.85 degrees is to B. If I do some basic cross multiplying, B times, not B equals, but B sine 55.49 degrees is equal to 17.2 sine of 46.85 degrees. I can then use the division to get B by itself and say B equals 17.2 times the sine of 46.85 degrees. Seems we had a runaway marker there for a moment. Divided by sine of 55.49 degrees. I will get a result that works out to be B equals 15.23 units. And this is a case of where I was given an angle, followed by an angle, followed by a side. So law of sines can be used to find angle, angle, side. My second example will be an angle side angle, where I know the angle for A is 108.43 degrees. I know my second angle is B is 45 degrees, and I know side C, which is in between them, is 10.2. Except that the one side that I do know does not actually have an angle over here that I know. So it seems I might be violating my number 2 question. Actually, I'm not. If I just do some basic geometry, which says that there's 180 degrees in a with the three angles of the triangle, and I subtract my 108.43 degrees, and I subtract my 45, you will come up with a total of 26.57 degrees, which would make, let's see if I'm successfully able to erase this. Oh, yes, I am. I can put in 26.57 degrees here. You take into account my 10.2 here, and I can set up my ratio saying that sine of 26.57 degrees is to 10.2, okay, and now here's the question. Do we want to solve for, let's say, side B? Do we want to solve for side A? For this case, I'm going to solve for side A, and the only reason I'm going to do that is I know that when I'm done, 108.43 degrees is the largest angle, so therefore I expect A to be the largest side. So if I actually was to find B, it should pretty much go A is the largest, B is the next largest, and then C would be the smallest. So we'll just go for the largest for the sake of, well, going large. And so I would say sine of 108.43 degrees is to A. The work is essentially the same as my first problem. A sine of 26.57 degrees is to 10.2 times the sine of 108.43 degrees. I will take A, I will make that equal to 10.2 times the sine of 108.43 degrees. I will go ahead and divide that by sine of 26.57 degrees. And it says that A is 21.63. So there you go, 21.63. which is definitely larger than 10.2. You know, just to prove that 45 degrees will be produce the second largest angle, let's go ahead and set this one up. And again, we'll just simply say that the sine of 26.57 degrees is to 10.2 as sine of 45 degrees, which ironically you already know to be radical 2 over 2, but we'll just do it, you know, on the calculator we normally have. I'm just going to cut right to the chase. This means that B is going to equal 10.2 times the sine of 45 degrees all over sine of 26.57 degrees. I come up with an answer of 16.124. So 16.12, and like I said, angle A is the largest, therefore has the largest side opposite of it. Angle B is the second largest, therefore it'd be the second longest, and angle C is the smallest, therefore it has the smallest side. The next example will be a side-side angle where I happen to have on this side A will be of length 11.7, length B would be 22.47, and angle A, which is 28.46 degrees, and more importantly, opposite 11.7. So I can use that particular ratio of sine of 28.46 degrees is to 11.7 as, and since I do have side B, I guess we'll figure out what angle B is here, and we'll say sine of B is to 22.47. So with a little cross multiplying and then dividing by 11.7, I can determine that the ratio of sine of B works out to be 0.9152. So if I use the inverse function, it says that my angle of inverse B would be 66.23 degrees. And you would think you would be done because you visualized the blue triangle. The problem with the law of sines, and this is the big catch, the formula may be pretty easy, but the problem is the answer only gives the inverse sine function only gives angles back that go from negative pi over 2 to pi over 2, which is the first and the fourth quadrants as we've previously discussed. And so up here you have something that's like 0.9152 as a y-coordinate for the ratio. But if we were to actually look at a unit circle all the way through, not only would at 66.23 degrees have a y-coordinate of 0.9152, but you would find out that on the reflection with respect to the y-axis, which would be 180 degrees minus 66.23, or as we like to say, 100. If I drew this out, you have to remember that, let's put this in red, that if I would go all the way from here to there, that would make that angle 113.77 degrees. That also has a y-coordinate of positive 0.9152, which leads us to a problem. Since that angle happens to be within 180 degrees, why could that potentially not be the triangle? And in fact, what we're finding out, as I hopefully am able to move to the next page, let's see here. If I actually tried drawing a triangle out that still had 11.7 could still be this side, not this side. I could still have my 22.47. I could still have my 28.46 degrees, but instead of having a 66.23 degree angle, I could actually take and have in this spot a 113.77 degree angle. It would be obtuse and still be able to come up with the triangle. And that's, again, why it was important to understand the Supplements Theorem. Supplements Theorem from the last unit, which said that the sine of pi minus theta, or more importantly in this case, sine of 180 degrees minus theta, could also equal sine of theta. And so what that says is, yes, I could have had a 66.23 degree angle, but I could have also had a 113.77 degree angle. Now this one I know works. The question is, could this one still work? Well, based on this drawing I've shown you, it definitely can work. But a lot of times in these problems, you don't actually happen to have the triangle drawn right in front of you. So you have to ask yourself, if you start with 180 degrees and you subtract the angle that you already know, which is 28.46 degrees, that leaves you 151 degrees to work with. We already know that 66.23 can work, and in this case we could have used 113 degree as well because we had enough room for that degree. So in this particular problem there are two answers. Let's go look at one more side-to-side angle problem to make sure we understand what might or might not happen. If we say that side A is 13.89 and its angle opposite of it is 77.08 degrees, first we have enough to establish the ratio. Sine of 77.08 degrees is to 13.89. So if we come around to side B, which is 8.6, and we are trying to establish what B is, we can say that the sine of B is to 8.6. And when we do our cross multiplying and then divide by 13.89, we will find out that the ratio works out to be 0.6035. And if we were to type it into our calculator as a sine inverse problem of sine inverse of 0.6035, we would be getting a specific angle of 37.12 degrees. But remember, this answer only goes from negative 90 degrees to 90 degrees, and so therefore there is potentially another angle that could work. So we know that one answer is 37.12 degrees. What about the second answer? What about, and how do we find the second angle? First is that we go 180 degrees and we subtract 37.12 degrees. We realize that that angle is 142.88 degrees. This is, of course, the supplementary angle. So in the last problem, both angles worked. How about now? Well, realize that a triangle has at most 180 degrees. If you use 77.08 degrees for one angle, the most you're going to be having left for the remaining two angles is 102.92 degrees. Well, you can easily get 37.12 degrees and another angle into 102.97. But if you only have 102.97 at most, there's no possible way you can have a 142.88 degree angle along with a 77.08 degree angle. So there's just no possible way that the supplementary angle works. And so if this doesn't work, you can just eliminate from the picture. And since that worked so well that time with me doing it, it seems to do it again. So in this case, the only answer is 37.12 degrees. And so I could put 37.12 degrees here. I've kind of done some of the work already for some of this other one. I think it's like 65.29 degrees. My handwriting's a little sloppy. That may not exactly be a 5. And C ends up, we're supposed to work out to exactly a 13. But in this case, there's only one angle. Again, if I go back and I hit the previous page and we look at this one, please note you have a 66.23 degree angle and you have a 113.77 degree angle. Each one fits within the parameters of 151.54. You can squeeze this one in, you can squeeze this one in. That means you have two possible answers, why you had originally a blue triangle and the red triangle. In this second example, you cannot get the second angle to work of 140 degrees, so therefore the only answer is 37.12. And that's the catch of the law of sines.